Hello boys and girls. So this whole video is really dedicated to understanding the standard logarithm function on its real domain. You know, the inverse is the exponential function, which maybe people find less spooky. The logarithm is this diffeomorphism, but also is a transcendental function, and I think a lot of people are uncomfortable with the limits that get you there with the form of the function itself, and we want to understand it, and we will basically do this in a somewhat algebraic way. We will on one side of the coin do not talk directly about the real number line, but we will construct, and you see this already a little bit on screen, we will construct certain algebraic structures, and we will incrementally build towards the nice diffeomorphic property that the standard logarithm has. We will, to get there, talk about sequences of functions which are more algebraic than a logarithm and play a role also here in statistics. And we will not only talk just about one sort of deformation. We will see various, and we will get a feeling for, like, you know, why they look like they look. This is basically the main point, to get comfortable and see how in deformed Q variants the property of the different properties of the logarithm look like. I am in part motivated. You know, I just made a video on temperature for math and comp sci people, is what I called it, temperature and entropy, and I will make a future video on the justifications that have been brought up to characterize the entropy axiomatically, and counter-arguments and arguments for it. I will mention also a little bit of statistics in this video, but mostly it's going to be fairly algebraic in flavor, and I will just mention its connection to information theory on the side. Okay, so, and with that said, let's jump into it. The script that we will discuss is split into a few parts. First, I front load a bunch of fairly abstract concept. The only thing that is an anchor point for the whole video, and also important for the whole video, is just, you know, fixing an integer n and taking a mathematical object to the power of it, a real number to the power of it. This sort of Frobenius map in a more, you know, finite field case, you might say. This map is like one anchor point. This will not change, but we will introduce deformations of basically everything else, and some weird idiosyncratic notation to basically make this diffeomorphism aspect more clear and see how the standard logarithm arises in the limit, right? So this is the program. We will start abstract, then I will get more concrete, and in the end talk a little bit about this generalized objects standard calculus. So you maybe get more familiar with why the logarithm has these properties that it has by looking at how things have to generalize if you generalize the definitions. Okay, so as I said, I will start out now with the abstract stuff. You can read what's on the screen. I define operations iteratively, and I, you know, to later get the point more across, I use this notation where I say multiplication n times I write as a product, and summation with itself n times I write as the sum symbol, right? I define this like in this recursive fashion. And these things, however, are really the super simple objects, right? So taking multiplying a g n times with itself gives g to the power of n. This is just notation. And likewise, adding y to itself n times gives y times n. If you wonder about the notation here, when I'm thinking in the multiplicative world, so to speak, right, in sort of the group world, we will later talk about the multiplicative group on the rails, I use the letter G to suggest group element. And when we are in the additive world, I talk about the output of output of the exponential function, input of the exponential function, and output of the logarithm. I speak of y, and you should really think of the y-axis on a Cartesian plane, where y is on the y-axis, and g is, if you will, on the x-axis, although this is not so important. And looking out for what part of the y-axis we want to speak about will play also a significant role in this video. So this is spoiler ahead. Okay, so I use these strange notations. I define just the inverses, which you can, easily invert these functions. This is taking the nth root, and the nth root will also be super important. Maybe more important than taking to the power of n will be taking the nth root in this video, because it is how you can better understand the logarithm itself, the structure, the form of it. And of course, dividing by n is the inverse of this sigma. The Frobenius-ish map has this nice multiplicative property. I will not go into complete detail with all the derivations. Some of them you can do at home in 3 lines, but let it just be said that this, of course, this algebraic property plays an important role in many of them. Okay, and here just a remark about the relation to the mean and the geometric mean. Okay. Yeah, so again, maybe burn this into your head, because this will be quite important when we set up the generalized logarithm objects. Here is some more notation. I will call the inverse of this multiplicative map, right, the nth root, taking the nth root. I will denote this by this very bold notation, like 1n. The idea is that if you think of n as a very large number, then on the positive reals, like g bigger than 1, this function for a very large n also converges to just the constant function 1. This is what you see here. I have a Desmos plot here open. Ignore for the moment everything except the... Oh, I have not even edited. Let me quickly. So I write x to the power of 1 minus capital N. This is just a root function, right? So if I take here, this is the square root function, obviously. If I take higher roots, so for example, the 12th root, then it gets closer to 1, and for n to infinity, apart from 1, positive numbers, this just becomes, here I'm at 23, and it's 23, and this is just the 1, right? And I define functions here parameterized by n, and in most cases you can just think of n as very large, and so the inverse of the multiplication with itself n times, i.e. the nth root, is just a 1. This is a handy notation because in a lot of formulas that we will see, the formulas might look complicated, but when you see a 1, just think 1, then you like a lot of things drop out, and you see the structure of these objects. Okay, and of course, the 1 has the same property as its inverse, and you can easily compute, just taking the derivative of this 1 function, and it comes out like this. And the fact that this derivative is simple also will play a role, right? This is literally just basically dividing by g. And you already might see the connection this has to the logarithm, right? The standard logarithm, ln of g, if you take the derivative with respect to g, it is 1 over g. This is basically the source of this. This sort of high root function will be the source. Okay. So, and now comes also the second, this is the most abstract definition. But it's relevant because this generality allows us then to go to this different statistic logarithm that I talked about, right? The Zales and so on. So we have this Frobenius map, multiplication of g with itself n times. And then take any, let's say, monotone diffeomorphism, tau. I use the letter tau, t, because we will take a function which maps 0 to 1, which maps between the units. But this in general is just any any diffeomorphism, and we define the exponential function like this, right? It sounds super abstract, but you will see, you already see like a spoiler where this is going. Now you can take the derivative of this object. It is not so difficult to get quite far, because g to the power of n, if you take the derivative, the n pops out and so on, and then you can use chain rule and inverse function rule to get this very generalized derivative. You get this thing here. You see already that if this tau is simple and this tau derivative of is simple, then this behaves already quite like the exponential function. The reason is that just so g to the power of n, if you take the derivative, then n comes down, this is this n, and we multiply it with some object to correct it, right? If you do not see this, I mean, we will need it only in special cases, but you can do this by hand and check this is right. The important thing is to already see how close this is to just the property of the exponential function, right? So here's a spoiler we eventually we're going to end up with for the Zahles version. If you have this shift 1 plus 1 over n times y, then the exponential function, our exponential function with n, is this thing, and you know this from the definition of the exponential function as a limit, right? And you know, taking the derivative of this is like just 1 over n, so n times the derivative is just 1. This is exactly this part here, so this immediately falls off, for example, in this special case. And also for large n, this is just 1, so you can see then that this exactly gives the exponential function. But we want to take care of studying actually this linear function later, or even generalizations thereof. And then of course, having defined the exponential function tau n, we define the logarithm as the inverse, like so. You can, even of this abstract object, take the inverse. We defined the inverse of the Frobenius map as this one map. And so the logarithm is really just the inverse of the tau map, which is simple, apart from some non-linearities that make our one function different from the actual constant function 1. And I remind you, the one function is basically a very high root, which is approximately 1. Okay, and now we can also take the derivative of this thing. This pops out. Here it still looks complicated, but it will become simpler. Here you already see sort of this derivative of the logarithm is 1 over g times some expression, which you know in the standard logarithm case is just 1. Okay, so this was the very abstract build-up. Now we go into the algebra part. If you have some bijection phi and some operation bullet here, then just algebraically you can define another operation, this plus operation here, right? And we are interested in using the multiplication, right? Because we are already using this Frobenius map, which is about real number multiplication. And we take our very abstractly defined logarithm. And then just from how this algebraically is set up, basically just from definition, you can, if you use all these nice properties, right? The tau of the our logarithm is just 1, basically by definition, and then use these nice properties of the 1 that I already discussed. We get this thing that you are very familiar with from the standard logarithm, right? So the logarithm of a product of numbers is some sum of the logarithms of the numbers, except we have not even specified yet what this plus really is, because it's like parameterized in terms of this general diffeomorphism, right? But this property of the logarithm comes easy just by using this Frobenius map, just by looking at this repeated multiplication, and then of course, the underlying plus here, this plus might be complicated, but we will see that it's in the end not even that complicated, and gives a very nice structure. Maybe I might go as far as maybe in some regards even nicer than the addition on the real numbers, but we will see what I mean. Okay, and here's again a sort of spoiler. We have already seen that taking tau 1 plus y over n gives the exponential function in the limit. And here is another sort of like deformation of this. Here, beyond what I just said, I introduce a gamma parameter, which we can play with. And of course, for gamma equals 0, this is just this example that I just talked about. For gamma equals 1, there's a square root, and it might look ugly, but it has actually some nice property, which I thought I would have written down, but apparently it didn't. So if you take this tau of y and multiply it with tau minus y, then you get exactly 1, because just how the algebra plays out. And then you get some deformed logarithm, which also has some nice properties. I might get later to this, but these are these two important cases which give us these statistics here. We'll get to this in a second. Here, is there a logarithm defined here as well? Yeah. Okay, we will see why this plays out like it does. So yeah, by the way, here also we can already take the powers. This already, like, even if tau is generalized just by the inversion properties of x and n, they are defined in terms of inversion, we already get this nice relationship of getting an approximate exponentiation just through these logs, which is kind of cool. Okay, so now you know that the logarithm and the exponential function have these diffeomorphic properties of mapping, addition, and multiplication, right? And now we will define our generalized log as, like, naively as doing exactly this. We get an input object g, to which we want to apply our generalized log, and we the g lives in the multiplicative world, the multiplication of positive real numbers, and we want to invert the multiplication gradually. We already have a map of multiplication, like pi product n to the minus 1. We already have defined this. This is just taking the root, and we will take away in the multiplicative side and then giving in the sum side. This is exactly what we do here. Naively, however, this doesn't really work out. You cannot just take the inverse and take and apply this sum, because then you get this thing. And I mean, it works out well, but you cannot take the limit of n to infinity, which is how we will get eventually the logarithm back. So this alone does not check out. This just becomes bigger for larger n, right? Because this thing is a 1, and this is repeated additions of 1s, so it's natural that this just would converge to something like n. What we hence do is we add like a counter term, a regularization, and here I set this up very general. We will specify, like, we will get simpler in a second. I subtract, so that it does not diverge, so that we do not add up ones, but we want to basically add up something which goes to 0. I subtract this object and define our logarithm up to some simple algebraic expression as n times, and then this difference of 1s, right? And now to remove this full generality, make it a little bit more concrete, we will immediately drop the complexity here, like you might let m go to infinity, or set d equals to 0. I hope this is not too abstract. Maybe think about it for yourself for a second. We will choose parameters so that the second term here is just a 1. And then the Thales log reduces to this object, right? So ln, or with parameters by n, is taking the sum part, like the repeated addition of a thing with itself. This is just multiplication by n of the difference of the inverse multiplication part, which is taking the nth root, minus, you know, the infinite many high roots. This is a different, this goes towards 0, right? If you take higher and higher roots, you go more and more towards 0. You subtract 0. This becomes smaller and smaller, but this becomes larger and larger. So this is this incremental. On all levels, it is basically like a homomorphism. You go away from multiplication with product to the -1, and you go more into the additive world with adding back everything on the additive side, and it comes out like this, right? Like my main point here in this video, like one of the main points, is really to you know, you might have seen this object before, right? I mean, you know already that taking limit n to infinity will get you to the logarithm, the normal standard logarithm. But my main point is to see that this is really this stepwise going, like taking away from multiplication and adding to addition, right? This is taking inverses on the multiplicative side and then adding back on the additive side. And in this way, the logarithm does this mapping. And in fact, this object, as we have just argued here in this definition, is also actually a homomorphism between multiplication, which we take away, and addition, a sort of form of addition in another world, which we will see for this finite n is not just addition on the real numbers, but it's some other structure. But in any cases, all these deformed logarithms are these nice structure preserving maps. Only in the limit is it between the positive real numbers and multiplication and the real numbers and addition. Here, are the axis of the coordinates. But even for the finite n case, this structure is there. Okay, here note, if m divides n, then just because this is a root, you get this nice property. This is already the property that you know, right, from the logarithm, that g to the m, you can pull the m out. This thing is less general than this thing, but it is nice because here you see if n goes to infinity, and this will become the logarithm for a fixed m, n over m still goes to infinity. So you see that this property shows up for the final logarithm in the end. So we got there to this, I will call it Zahles log, by considerations of inverting multiplication and adding additions. But if you now look at this expression, then you see in terms of what we previously defined completely abstract, you know, independent of this addition multiplication thinking, we get that this tau is indeed this linear function that I already spoiled, right? And I've already showed you that the exponential function, which we have abstractly defined with this linear tau, is this object. And now in our new language, where we speak of reducing multiplication and adding addition, the exponential function is exactly the other thing. It is like taking away addition. It's slicing up the y, right? Sigma to the power of -1. It was just taking y and dividing by n. It's taking a y, it's slicing it up into even smaller bits, but then adds on the multiplicative side back. And this is what the exponential function is. It's this homomorphism in the other direction, where you do not first take away from multiplication and give back in addition, but you go exactly the other way around. Okay, and why did I define this so like in this all this generality with these parameters m and d and so on and so forth? This is basically just to motivate that there are also other deformed logarithms of this shape which do not just take a -1 here, but you can also choose these other parameters. You choose d is -1, and you fix m to n, and then you get this sort of symmetrized logarithm, and this is then called Kaniadakis logarithm. And it has some nice properties. So for example, you can take the logarithm of 1 over p, where p is a probability, and this is the information in information theory. And with all of the logarithms, you get some deformed information there, the information quantity. The entropy is the expectation of the information. This is the basic information theory. And so we get, for every logarithm, we get a new form of entropy. And this logarithm with the kappa has the nice property that, for example, like the standard logarithm, it has the property the logarithm of 1 over p equals minus the logarithm of p, right? You can pull down this minus and nothing happens except that the input is taking the inverse off. I hope that makes sense. So we have just this nice like symmetry there, and that's why this one is also relevant. This Salis and also this logarithm here these are all fairly recent inventions, like later than the 70s. Okay, and now we want to study this operation that I spoke of. Again, our tau is this linear function. Notice that the kernel, the value at which this is 0 is minus n, right? 1 plus 1 over n times minus n. The n's cancel, and so this becomes 0. This is minus n is the kernel. I call it here y minus infinity for good reason. Because if you let me actually refresh this, because I've already fixed this up a little bit. If you take this the Thales log that we have just defined and use this kernel object, and it looks like this, right? It has a bottom value minus n, and then whatever you input is like this. If q is positive, if g is positive, then this is like some factor near 1. It's multiplied by n, and so you see the range of the logarithm in this form, right? There's a bottom value, and then you add some morphing which depends on q. And if you take the definition of our plus that we had above, right? Scroll up again. This was this definition. If you now take for phi the Thales log, and for bullet, of course, the multiplication, right? This thing, then what the operation actually comes out of is exactly this. So this addition between, I call this here y and z, is just standard addition plus, and then you have to do the algebra and check what all the things that cancel. It comes out that this addition is just normal addition plus, and then there's this product term, right? Or in our notation here, this is you can also do this calculation. You find this is exactly the bottom value plus n times, and then these linear terms. And so this is actually the addition which is in the range of the logarithm, right? You have the multiplication of real numbers g, you apply the logarithm, and then you get mapped into a world, into an algebraic structure where this is the group structure. This is an abelian operation, as you can see, which makes sense actually for values from minus n to n. So if we go back to this picture, I will now activate all the things here, maybe apart from the root. So again, sorry, I switch back. The our Zales log looks like this: n multiplied by the root minus 1. This is the logarithm. So here, this violet line is just this the normal square root, right? And if I go to the cube root, and it looks very similar. Maybe I add both of them actually. Yeah, so here these are just two roots. The logarithm is literally just taking the root, subtracting 1, so the whole thing gets a little bit down there, and multiplying by n, so it gets a little bit boosted. So for example, if I move this here, well, let me actually replace the square root with sorry. Yes. Let me just change the color. So I have now here the red moving part. This line, this red line is just the nth root. Whereas the logarithm, the other moving red line is here, is just taking the same function, subtracting 1, so it gets down a little bit, multiplying so that it's boosted up a little bit more, right? So the red moving parts are just the same function apart from a linear transformation depending on n. And if I disable those, the logarithm for n is this red line now. These are just various shifted roots. And for larger and larger roots, if I go to n, then because the multiplication to the minus 1 and the addition n times fight against each other, the root does not go to the constant line 1 anymore, because I multiplied by n, but it goes to a certain value, and this green line here, and this green line, the limit of it, I mean, almost in the limit, it's something very close to the green line. This is literally just a logarithm, right? So as the formula says, the logarithm is just taking the infinite root, but multiplied by bumping up of n, also infinite. So this is this function, and if you take any g on the real number line here, let's say 4, you apply the logarithm, you're mapped to some number on the y-axis, and on this structure from, like here I have the, let's say have the ln logarithm with n equals, let's say 3, okay? Then the range of the y on the y-axis from -3 and not lower to any positive number on the y-axis is this domain of this group structure with this strange O plus addition, right? And of course, if you go with n to infinity, then the operation that we had here, if we go n to infinity, this just becomes 0, and eventually the addition on the group structure on these on the y-axis just becomes addition, and then the whole thing just looks like the real numbers with addition. But for smaller n, you have just an operation which goes from this point, minus n, to infinity, and with this strange operation, which is in this homomorphic relationship to just a multiplication on the real number line, right? So you understand now that for finite n, there's also this deformed addition structure on the y-axis, which the logarithm is the object that maps multiplication on the x-axis to. Okay, I know maybe this was a little bit like I said the same thing a couple of times, but I want to get you this geometric picture in your head, right? That this logarithm, that is an algebraic function. It's not a transcendental function. It's just taking the nth root, well, taking the 15th root, for example. Maps the multiplicative structure to a very simple abelian group with this multiplication or addition, right? Group operation. yeah, here some simple calculation that show that the 0, right? So the 0 point, this point here on the y-axis, is still the 0 point with respect to this addition. But unlike the addition on just the real numbers, this addition has an absorbing element, right? If you plug in minus n, then this is like adding y plus t equals minus 1 times n. Then oh no, the other way around. So if you plug in for example, I mean, we can do it like this, I guess. Yes, exactly. So if t equals minus 1, then you add minus t, and then these y's cancel, and I'm left with minus n, right? Minus n. And so this is an absorbing element which you do not have in the real number addition. If you take the limit n to infinity, then this addition becomes the normal addition, and the absorbing element would be the minus infinity on the extended real number line. If you want to talk in terms of the extended real number line, then there's still an absorbing element, I guess. Okay, and now we've understand this algebraic structure. The rest of the video is fairly simple. I will just show you how the Thales log connects to the real log and how the generalized properties look like. So firstly, sorry again for scrolling so much, this structure n times n root minus 1, if for n you use maybe 1 over epsilon or something like this, then you see that this the limit of n to infinity is exactly like taking a derivative, which looks like this. It's like taking the derivative of this this form, and if you plug in for g to the t e to the t logarithm g, then you see that the logarithm comes out. So this limit is computed. Of course, this works for this other logarithm that I've defined as well. This exponential limit is even similar, easier, because the you have seen where is it? We have seen this limit taken to infinity a couple of times, right? And it's also the inverse of the logarithm, so that should be clear. Okay, and here you can read this off. There's a bunch of nice properties that tell you that the logarithm is actually not even that bad in terms of divergence at 0. Okay, and so here I write down some of the very familiar expansions, Taylor expansions. Some formulas, I actually yesterday just plugged a bunch of these into ChatGPT and ask it, hey, I know there is some deformed versions of this Taylor expansion. Does this also exist for some other series? It does not exist. Like some nice generalizations do not always exist, but the ones you see on the screen are those that exist. If I take this tau and define this, deformed factor for n to the infinity, this just becomes 1. Then we still have the standard Taylor expansions of our x and our logarithm. From these, it's very clear that for n to infinity, that these go to the standard expressions. We have, if you take the standard exponential function, then our ln of the standard exponential function is still approximately the inverse, as you would expect. Above I showed you what the derivative of our 1 is, and our logarithm is defined literally as n times this 1 minus a counter term. So it's also easy to compute the derivatives. They look all very nice. For this, you see that for n to infinity, this goes over 1 over g, as you would expect. For the second derivative in two different directions, you get this expression. For n to infinity, this is 0, and this is one of the debated aspects in the axiomatization of the entropy. This was a motivation why I even started to writing the notes on this. You see that the second derivative in two different directions of the product of the logarithm is not exactly 0, only for the limit n to infinity. And this corresponds to a certain, like, you can argue that this corresponds to a sort of local independence property. If independence of probabilities means that their joint probability is just a product of probabilities, right? If these are probabilities, then local independence corresponds to, going in one direction is independent of whatever the value of the other is. Whatever. This is not part content of this video. I might make a video on this, but just to observe that the second derivative of ln is easy, but it's not that easy. Not as easy as for the final real logarithm. And then for completeness, I write it down for the Kaniadakis logarithm as well, what it is. It converges a little bit faster even, this symmetric logarithm. And finally, I've also written down some standard integrals. So, the logarithm, is, we know what the derivative is, so we can also say the logarithm is, we can define it as this integral over 1 over u. If you have not taken the limit n to infinity, then it looks like this. Or more generally, you have this relationship. And then there's also like a standard result, a standard integral, where you take logarithm of x to the power of n. And you get something nice out of it. And I just also looked up the generalization of that, and it comes out like this. Okay, so to summarize, I think the main takeaway from this video should be, on the one hand, what is the logarithm? Well, a logarithm is really, even if it's ugly, even if it's naively ugly, the logarithm is basically this thing, where you take the input g and you remove you slice it up in multiplicative space. You take high roots, and then you've made it small, then you make it bigger again, but not in the multiplicative sense, but in the additive sense, right? This thing here where you take the inverse of the product and then take the sum function. This is the logarithm. And just so to make it converge, just to make it not go to infinity, you add a counter term. And depending on what counter term you take, you get different deformations of logarithms. Even if you have finite n for the Thales log, you can define the algebraic structure here, which you should think of a certain group property on the positive y-axis down to minus n. And it is such that this is like a root. This is not transcendental. This is literally an algebraic property of some strange group addition. And if you take the limits, then the property of being this diffeomorphic property still is preserved. You're still mapping two algebraic structures together, but the O plus just becomes the simpler addition. This is the main thing. Okay, so I hope this was informative. This was the more algebraic part. In the last part of this series, or maybe I do two more on the entropy. I will put things together and show you the argument for why the entropy should be different in terms of the logarithm, or why this might be asked a little bit too much, and why you could also just take some other deformed logarithm, right? The logarithm has this property that if you plug in a 1, you get 0. This is true for the Thales logarithm as well. So meaning if you have 100% certainty, then there's no surprisal. And the in the other direction, if something is unlikely, then you have high diverging surprisal. And if you take another like a logarithm, then you get another entropy notion. If you take the Thales log and do the standard Lagrangian optimization, you say I want to extremalize, maximize the entropy with this and this logarithm, having mean fixed or having mean and variance fixed, then you get certain standard distributions. For the standard logarithm, you get the exponential Gaussian curve, you get the standard normal distribution. For deformed logarithms, you get deformed normal distributions, which are the in the case of the Thales logarithm for at least for n larger, like larger than 2, you get the student t distribution, which also very naturally show up in certain considerations of statistics where you do not know the variance and have to estimate the variance and so on and so forth. Here you see that for higher parameters, higher degrees of freedom parameters in this parameterization, the student t distribution is actually, you have less, like it has a higher variance, you have less knowledge there than on the I'm using not the perfect vocabulary, right? You optimize with respect to a certain variance. With the Thales entropy, you get a certain distribution with this variance. But this the parameter fixes different distributions, which here in this sense have different parameters there. I will not probably talk about all the different connections between the Q Gaussians and different parameterizations, but just let it be known that if you choose the parameters correctly, you get basically the same families of functions out of it. And I'm just wanting to emphasize that they are standard and important. Even if you do not do Thales entropy, you might run into the T distribution, student C distribution. Okay, I'm talking too long. I hope this was informative, and I'll see you in the future.